Hello, I am Kyusok Jung, and I'm going to present about color center, nitrogen vacancy center in diamond. Contents are as follows. In the case of a general computer, bits are used as information units. For bits, store information as 0 or 1 and perform calculations sequentially. In contrast, in the case of quantum computers, qubits are used as a unit of information processing. This is much faster than a general computer because it stores information in a state of superimposed 0 and 1 and performs calculation at the same time. Let's look at a concrete example. A general computer requires 2 to the power of 55 bits to represent a 50-digit binary number, whereas a quantum computer requires only 50 qubits. One of the ideal materials for building a quantum computer with such excellent computational power is the MV center. The MV center is used as a single photon emitter in a quantum computer. Then, what is the MV center, a key element of a quantum computer? To know this, we must first look at the structure of the MV center. The structure of the left is a normal diamond, and the structure on the right is MV0. In the case of MV, it is a kind of point defect, and it has a nitrogen substituted in carbon and a vacancy structure next to it. They formed a nearest neighbor pair. Looking inside the MV0, there are 2 electrons from the lone pair of nitrogen and 3 electrons from the vacancy. So there are a total of 5 valence electrons. If external voltage is applied to MV0, which is electrically neutral, electrons are trapped, and it changes to MV- with 6 valence electrons. This MV- is used to build quantum computers. Before understanding the energy state of MV-, we need to know about singlet and triplet. An electron has a spin quantum number of +½ or -½ depending on the direction of the spin. A particle system with 2 spins has a total of 4 basic states, of which 3 have a total spin angular momentum of 1, but one has a total spin angular momentum of 0. Here, the former one is a triplet, and the later is a singlet. This is strongly related to the energy state of the MV. Now, let's look at the energy state of the MV- center. The energy state of the MV- center can be divided into 3 main categories. The lower left part is the triplet ground state, and the upper part is the triplet excited state. Here, each is divided into 3 types according to the combination of the spin direction of the electron. In the absence of an external magnetic field, the 2 states with MS equal ±1 are degenerate. The right side is a single metastable state with energy between the 2 preceding energy states. When energy is first applied to an electron in the ground state, it is transferred to an excited state. In this case, 2 major transitions occur, respectively, a radiative transition and a non-radiative transition. Radiative transitions preserve spins and emit photons. In case of non-radiative transitions, spin changes and photons are emitted. We can use the MV center as a single photon emitter by using a radiative transition. In addition, where an external magnetic is applied to MV-, the Zeeman effect occurs, like this. There is no change in the case of MS equals 0, but in other states, the degenerate state is reversed and an energy state splitting occurs. In this case, since the energy of the wave emitted by the electron is changed, the applied magnetic field can be identified by analyzing the optics. That is, the MV center can also be used as a magnetic field measuring device. Finally, we will look at the advantages and applications of MB Center. First, since the MB Center is bright enough to be detected with a microscope, the state of the MB Center can be easily read. Second, since it has a long coherence time even at room temperature, it can be used at room temperature. Unlike quantum computers that require a cryogenic environment. Last, the color center of diamond is optically individually characterized, so making it easy to build scalability at quantum computer. Other applications of MB Center are shown in the following pictures. The reference is as follows, and thank you for listening.